Well, greetings, everyone. So last time was sort of the introduction to the course, overview, and some of the logistics. Today we'll get into the real content. In general, I'm not going to spend a lot of time in this course making announcements and things, but for the first few, I want to just make sure people are clear. So, as you know, this coming Monday is Labor Day, and so there's no classes, so therefore you won't have recitation sections. But we are scheduling what we call a Linux boot camp on Monday evening at 7 p.m. This is completely optional. If you have experience in Linux or command line activities, and sort of generic, how do you get code to run, how do you edit files, how do you move files around, will be covered. We'll also cover some on Git, because we're encouraging you to use a Git server that's operated by ECE. And by the way, people have various ways communicating us. They're having trouble with that. And the honest truth is, it's not all set up yet. My understanding is the person in ECE who runs that is at Burning Man. And he goes there every year, and they have the same trouble every year. So hopefully he'll have a really great time there. Come back, well rested, fix things up, you'll be ready to go. Hopefully by the time of this boot camp. Like I said, this is we'll do over the course of this term a few of these evening sessions, review sessions. None of these are mandatory at all. They're here to help you. We may or may not record them in video. We will, in all cases, post whatever materials were passed out or used, like if there were slides or code samples or something like that, will be made available on our website. Also to mention, as I mentioned last time, there is a new lab for this course called Lab 0. It's intended to be a walkthrough of basic C programming that hopefully you already are fairly comfortable with. And so it really should take much time, 1 to 2 hours potentially, to do it. And we encourage you, this will be due a week from today at midnight. We encourage you to get going on that right away. You don't need an Autolab account, you don't need a GitHub account, you don't need much of anything except access to the files which are on the website and to some type of machine that you can compile and execute code. I've tested it on my Mac and on Linux. I don't think it would work directly in Windows because it makes use of some Linux libraries, but if you have a Windows machine and you want to set it up, there's a open source software called Cygwin, C-Y-G-W-I-N, that you can create a sort of Unix-like environment on a Windows machine. And this is one, we have this elaborate system of late days and grace days and so forth. None of that applies for this first assignment. You either get it done or you don't. It's intended to be more of a assessment for you to understand whether you've got the sort of programming background that sort of minimum programming background we'd expect for this course. The other is those of you who aren't officially in the course yet or perhaps on some wait list, please don't contact us, the instructors, about waitlist issues, because I don't even know how waitlists work. We're working with the course administrators, both in CS and ECE, to deal with these, and they are much better equipped to deal with it than we are. Okay, that said, let's move on in. And this material we're going to do in 3 lectures, cover all of chapter 2 of the book, which if you open up your book and you count pages, you're going to see a lot of pages there. So it's a pretty fast move. And these lectures will not duplicate or completely cover every bit of material there. It's the kind of thing, none of this is super advanced math, but you have to get really comfortable with this. Is very foundational material you have to be very comfortable with to move on to other parts of the course. So you've grown up in an era where bits are a sort of a fact of life. It's interesting that the term bit was only actually first developed in 1948 or so by a fellow named Claude Shannon, who didn't invent the bit, but he invented information theory, which defined the sort of most primitive piece of information as a bit. And of course, you know that everything in a computer is sort of organized and expressed in terms of ones and zeros. I don't know if you've ever sat back and thought, well, I wonder why they do it that way. And the answer is, well, there are reasons, but it's not the only way you could do it. For example, the first computer, sort of large-scale computer, was this machine called ENIAC. And they used vacuum tubes to implement it. It was a very large, heavy, expensive machine. And they encoded everything in decimal using one vacuum tube, basically 10 vacuum tubes for every digit. That would be, if you think of them as on or off, it would represent which of values 0 through 9 is one of those vacuum tubes we have. So it wasn't always the case that powers of 2 were sort of the dominant way of thinking about even computers. But nowadays it is, of course. And there's a few good reasons from a sort of systems design perspective. One of them is that in terms of electronics, if you actually hook up an oscilloscope or some other meter to the signals, like going in and out of your chips or somewhere, you'll see that they're not these perfect, smooth, square lines. They have bounces, variance, and similarly the devices that we build circuits out of, as you know, are extremely small and not that well engineered as far as nice, clean responses and things. And so the advantage of doing everything in powers of 2 is, or bits, is that you can deal with a lot of noise or uncertainty or imperfection in the system and still reliably extract from it a signal of either 0 or 1. And especially for storing information, we won't go into it too much in this course, but you can imagine there's some circuits that have feedback loops where you can either be feeding back a 1 or feeding back a 0, and that's a very stable value. Whereas if you try to discretely represent more values than that, then decay or noise or various other sources can corrupt those signals. So it's become sort of a matter of course that everything we do is in terms of ones or zeros. And it's important to understand that there's nothing in a bit or a bit representation that tells you, for example, this is a number, or this is a string, or this is a floating point number, or this is a piece of code. The bits are just bits, they're just values 0 or 1, and it's how we assign meaning to those bits that determines how we interpret them. And that's sort of a general abstract statement that we'll keep coming back to at multiple points in this course to make sure and really reinforce that idea. So for example, we could represent a number like 15,213 as a string of ones and zeros and use a base 2 representation of it. And we can think of numbers that are decimal numbers, but we can represent them again in base 2. And in this case, and we'll talk about this a week from today, we no longer call it the decimal point, though. We call it the binary point, where the marcation is between values that have a weight of some positive power of 2, like 1, 2, 4, or 8, and ones that have a negative power of 2 weight, like a half, a fourth, an eighth, and so forth. And so actually when we represent floating point numbers, we're using a base 2 representation. So the floating point number 15213.0 is represented as a binary number, but with a binary point, and then weighted by the 2 to the 13th, which is what it takes. It has nothing to do with 15213. It has to do with what it takes to get a number that's somewhere between 1 and 2, scaled up to be 15,000. So again, these are fairly straightforward ideas, but you just have to keep coming back to this all the time. If I see a bit string, I can't know in advance whether it's one number or another, or what its representation is. And I can interpret it in different ways. So there's various ways that you can represent small or bit strings. You can write it all out in binary, but that gets to be kind of cumbersome when you have, say, a 64-bit value to write out a string of ones and zeros. And so what we'll typically do in this course, and it's fairly commonplace, is to pack them, sort of group them into 4 bits at a time, so that's some value between 0 and 15, if you think of it numerically. And we'll represent that as a single digit in hexadecimal notation. Hexadecimal meaning power of 16 representation. And rather than suffixing numbers with what base we're using, we'll do it the way it's written in C, which is to say that we'll just prefix something with a 0x. It can be an upper or lower case x. The letters in there can be lower, uppercase, it doesn't matter. But basically, we'll use the digits 0 through 9 plus A through F to encode these 16 possibilities. And so one of the things, skills you will acquire in this class, whether you want it or not, is the ability to fairly easily go between a bit pattern and one of these 16 characters. Which sounds like a strange skill to acquire, but it's actually quite useful. So for example, the way we'd represent the instead of writing out 15, 2, 13 in binary, we would group that by saying, well, 0, 1, 1 is 3 on this table, and 1, 0, 1, 1 is D, 0, 1, 1 is 0, 6, and 1, 1, 0, 1 is, I'm sorry, B and then D. By the way, my trick on this is I've memorized 0 through 9 is pretty straightforward. I know this is A, I know this is C, and I know this is F, and I kind of interpolate the other ones between it. That's when I don't have the table hands. If you're stuck on a desert island, having to encode things in hex. Interesting quandary to be in, right? And so one of the things, we'll keep coming back to this, when we're looking at typical values on a machine, there is no standard. There's no uniform standard. And so people will talk about, well, what's the word size of your machine, and is it a 32-bit machine or a 64-bit machine? You'll hear all those terms thrown around, and the truth is, none of those are very meaningful. In particular, like this Windows machine or my a standard, basically, Intel microprocessor, is actually the hardware in there is built to support 64-bit operations on integer operations, addresses, and so forth. But it can also run in a compatibility mode that goes back to actually along the early 90s, where the machine only supported 32-bit operations. And so we'll talk about a 64-bit machine and a 32-bit machine. But the truth is that this one machine is both. And that's true probably for most of the machines of any sort that you'll encounter these days. And so it's really a combination of the operating system, the compiler, what code it generates, and the hardware itself that determines what the machine type is. And that's so you can actually configure when you compile code, and we'll go into this, whether it should generate 64-bit code or 32-bit code on most of the machines you'll deal with. So, and you'll see that the basic C data types, for most part, are independent of whether it's 64 or 32 bits, except for when you put the, say something as a long, you'll see all of a sudden it flips from 4 to 8 between, depending on which execution model you have. And similarly, the pointers, and this is where it really counts, 4 bytes is a standard address on a 32-bit machine, and it's enough to give you a range of about 4 gigabytes of memory, which, when that came along, that was a lot of memory. But nowadays, of course, a lot of machines have more than 4 gigabytes of DRAM in them. And so that's part of the reason why things have really shifted over to 64-bit, where now the range is far greater. Again, we'll keep coming back to this. So down at the lowest level then, as I said, we're operating on bits. And the same guy who invented information theory, Claude Shannon, did a master's thesis in 1939, that, or 38 or so, that was like considered the greatest master's thesis ever. Because he linked up the idea of Boolean algebra, which had been developed by this logician in England in the late 19th century named George Boole, with how do you design digital circuits. And so the idea of Boole was trying to codify what we call propositional logic, reasoning about true and false things, as an algebraic form, sort of making it more like math than like something that's sort of an abstract philosophical concept. And so his idea is think of 0 as like false and 1 like true. And now we can algebraically introduce an operator like AND that gives you a true value only if both inputs are true. So A and B means both A and B have to be true. And similarly OR, well, either A or B has to be true. So if both are false or 0, then you get a 0. And same with negation, you just flip true and false. And there's one called exclusive OR that we distinguish between inclusive and exclusive. We say exclusive OR means one or the other is true, but not both. It's interesting in English, we kind of informally can blur that distinction between inclusive and exclusive. I can say, would you like me to cut off your left hand or your right hand, right? And there's sort of an implicit understanding that I'm not going to cut off both your hands. So if you think about how you use or in ordinary discourse, sometimes you mean inclusive and sometimes you mean exclusive. But we'll distinguish those, obviously, as two different operations. So back when Shannon did this, actually, it was back when instead of transistors, they had relays, electromechanical relays, and they built these remarkably complex systems, like the whole telephone switching network, out of these electromechanical relays. And he was the first to kind of come up with basic principles that you can take this network of relays and systematically derive an expression describing when you're going to get a connection from point A to point B through this series of relays. It makes you wonder, how did they do this before he thought of this? So it's one of those interesting things that after the linkage had been made, it was so self-evident that we can't imagine any other way of doing things. We can generalize then from just a simple 0 or 1 true false value to basically a whole string of bits, or what we call a bit vector. And if you think about a word on a computer, you have 32 or 64 bits, we can think of those as not just representing a number, but just a string of zeros and ones. And when we can apply these same operations to strings of bits, so we say, and they apply now on a bit per bit basis. So if we have an and, we have to have a 1 in both elements in the column in order to get a 1 as our result. And similarly for other operations. Nice animations, by the way. Would apply. And so you can see again, or you have to have one or the other. And the same kind of reasoning principles that the sort of simple 0-1 case applies to mostly holds for the string of bits case too. Now that one of the actual very practical uses of this is for thinking about sets. So imagine that you have a maximum of 32 things. And so you want to represent different sets or subsets of those 32 different things. Well, you can just use a bit string of length 32 and say it's a 1 if a given element is there, and a 0 if it's not. And then use, now when you think of and, that becomes like intersection of two sets, or becomes like union, and an exclusive or becomes what they call a symmetric difference between the sets. So this is actually used a lot in real life in computers, and you'll come across this, that we'll want to keep track of how many different network connections are we maintaining at any given time, and be able to selectively say, I will accept an incoming message from any of this subset of the possible connections. So there's actually a library that lets you create these sets and manipulate them. But underlying it all they're doing is using these words of bits, one or multiple words, to indicate them. And so it's this is sometimes called a mask. When you have a string of ones and zeros, the ones are the positions that you're kind of interested in right now, and the zeros are the ones that you're not interested in. And you use an AND operation then to just only look at the items of interest. So this is sort of a very practical thing, but it's also a very important from a mathematical sense. And there's actually a theorem called the Stone representation theorem, due to Mr. Stone, that said there's a sort of one-to-one mapping between an arbitrary set, has to be countable, and basically a bit vector representation of that set. So in C, and in actually most contemporary programming languages, you can actually make use of those operations. And you're going to get some serious heavy-duty experience with this in Lab 1, which will be out next Tuesday, by the way, of learning how to love or hate, or at least make use of these bitwise Boolean operations. And so the symbols that were used earlier for and, or, and exclusive or are exactly the ones that C uses for these bit-level operations, and tilde for not as well. So for example, we can look at some 1-byte values. So 1-byte values can be represented by 2 hex digits. And we can look at, well, what would these operations be? And unless you're like a real hex wizard, you probably can't just do that straight away, like what the complement of 4 is. But you could use the table and cheat. But what you can really do is write it out, there is a binary expansion of 4 and 1, then you invert those bits, and then you go 1, 0, 1, 1, and you'll find that in the table as a B. And similarly, 1, 1, 1, 0 is an E. So hex is sort of a convenient way to write things out, but not a very convenient way to reason about things. Was there a question? Well, it's a char data type. So remember, all computers nowadays can represent various different sizes. So the underlying data type char, C-H-A-R, sometimes called char, is 8 bits. So yes, you have an 8-bit computer. You have many of them in your lives, but they also often are 16, 32-bit, and 64-bit computers too. Question?
Could you just like subtract that digit from 15?
Yes. Same thing. If you think about that subtraction of, if you take all ones, 15, and subtract it, you don't have any carries or borrows, so it will be exactly the complement. And that's a useful way to think about bit level operations. And similarly, I can say the complement of all zeros is F. Actually, I could do that one in my head pretty easily. And other ones, again, you can drop down to bit level representation, map it into the result you're looking for into bits, and then convert back to hex. This class isn't really going to be about, like some people can actually do addition and multiplication in base 16 in their head. I can't do that. And I figure if computers can do it, why should I learn? Now, one thing that's a common gotcha in C, both because people don't know the difference, or they do and they forget, or they make stupid mistakes like I do all the time, is that there's some other operations, like another kind of and another kind of or and another kind of not in C. And they're really, really, really different from the single ampersand version. So in this logic, which is a different logic, there's only two values. Something is either false or it's true. False is only way to represent it is the value 0, but anything that's non-zero is considered true in this context. And so when I say something is and, if they're both non-zero, then they're both true, and I'll generate the value true, but the value I generate will always be 1. So this is actually a useful, we do it all the time, but keep in mind underneath it, it's a kind of a funky way to think about things. So if we negate the value 4, 1, we get 0, because 4, 1 is, and by the way, don't make the mistake of calling it 41, because it's not. It's 4, 1, because it's base 16. Anyways, 4, 1 is non-zero, and so its complement is false in this logic. It's a different thing, and that means 0. And on the other hand, 0, it's not negation in this sense, is just the value 1. And so, in fact, one of the tricks you'll use in your first lab is if you do 2 knots, by the way, I always just say bang here, bang, bang, of a value. It's a way to convert it. If it's 0, it will stay 0. If it's anything non-zero, it will convert it to 1. The other thing that's important about these operations, both the and the or, is that they have a sort of early termination trick. And so you can say, for example, this bottom one says, if I have a pointer called p, I can safely say p ampersand ampersand star p. And what will happen is, what will this return if p is a null pointer? 0. And it will know the result is going to be 0 because 0 and anything is 0. So it won't actually evaluate the star p. And that's good because if p were a null pointer, then star p would give you an error. So you'll think about and you probably know this already, that if you have a long sequence and you use ampersands or vertical bars to denote it, it will only evaluate as much of the expression it has to from left to right in order to determine whether it's true or false. anyways, you've probably heard this before, but, and I make this mistake even now, not because I don't know the difference, but because I'm not a very good typist. So another class of operations that you probably haven't spent a lot of time using yet, unless you're fairly experienced, is shift operations. And you can say shift something left or shift it right. But the curious thing is there's sort of two different standard conventions for right shifts that will make a lot of sense later today or first thing in the lecture next time, but they don't make any sense at all until then. But I'll go over the rules anyhow. So in general, what happens when you shift something left is you just slide the bits over that many positions, and you fill the right-hand side in with zeros. And whatever, if there were, you'll basically shift off the end, whatever was in the first three positions on the left before, now will just disappear into nowhere. Shifting right, there's sort of two different conventions. The one that's sort of the natural one is what's called a logical shift, meaning I do the same idea. I shift some bits over, I discard the ones that are no longer needed, and I fill it in with zeros. But there's another kind of shift called an arithmetic shift. And what it does is it replicates the leftmost bit of the operand, the argument. And that's why in this example it's shown in red. And so as long as it's a zero there, then arithmetic and logical shift will be the same. But as this example shows in this second case, where there's a 1 in that most significant point, now when I do an arithmetic shift, I will fill in with 1s, which is not at all intuitive that's a useful or a good idea. But it turns out when these are representing potentially negative values, as we'll get into later, that's actually a very useful operation. It's a way to divide something by a power of 2, roughly speaking. So we'll see in just a little while why there's a distinction. Now, one of the, and as you know, in C, you can represent those shifts with double left, double less than or double right side. And whether a given expression will evaluate using a arithmetic or a logical shift is a little bit tricky. We'll talk about it later. There's only one way to do it left. The other thing that's just a general warning is there's no sort of strict interpretation in C of what it would mean to shift something by a negative number. Like you might think that shifting left by -1 should be the same as shifting right by +1, but there's no, that's unlikely your machine will do that. Similarly, if you say shift a number left by 32, or by say 100, you'd expect maybe you should get all zeros, but that may or may not happen. And C, as a language, makes no particular statement about how it should be implemented. And that's, by the way, one thing we're going to see with C as a language is that there's huge parts of it that are undefined, meaning that basically the compiler writer can choose how something is implemented, and it may not do the same thing from one machine to another. And that's kind of a disturbing feature when you're trying to write programs that are designed to run across multiple machines and compilers. That was one of the design goals of Java, in fact, was to make sure that everything was defined so that programs would be completely portable. But we're not using Java in this course, so we're going to be stuck with C and its quirks. So now, just sort of rolling along, there's two main classes of numbers we're going to, of integer numbers we're going to want to make use of in this course. And one is unsigned numbers, meaning values that are between zero or positive. And so we'll call those unsigned because they don't need a sign to say whether it's negative or positive. And then another class of numbers that we refer to as signed numbers. There's many different ways you could imagine representing numbers that may be negative or positive. But the most common by far, and the way we'll mostly consider, is what's called a 2's complement representation. And the idea of that is, if you look at it from a bit representation, an unsigned number is just a familiar binary representation that you have a series of bits, each is weighted by a power of 2. The 2's complement is the same idea, except the most significant bit has a negative value associated with it. So we'll show some specific examples of that. So let's look at 2's complement as the less intuitive one. So the number 10, for example, is just it's a positive number. So the first bit, the signed bit, will be 0. And you see that the weighting of those values is according to that formula I showed you before, that everything but the leftmost bit has a positive weight, and the left bit one has a negative value, a negative power of 2 value associated. And the other thing you'll notice is that negative value is more negative. You know, it's a heavy weight, let's say. Its magnitude is large. It's 2 to the w. The word size here is 5. So 2 to the w minus 1. 5 minus 1 is 4. So minus 2 to the 4th is minus 16. So we'd represent negative 10 then by saying, well, you start with minus 16, and whoops, that's sort of a little more negative than I want. So I'll add back 4 and 2 to that in order to get it to be minus 10. And that's the general scheme of things, that a negative number, we start by making it very negative, and then we add back positive powers of 2 to bring it back towards 0 to the value we're looking for. And so, for example, this table shows if you want to represent 15,213 or negative 15,213 as 16-bit numbers, then what you rely on is the fact that you can set this most significant bit to either 1 or 0, and it has a weight, in this case, of 2 to the 15th, or 32,768. So just using that very simple set of ideas, we can actually explore a lot about what numbers can be represented and what the representations look like. So for example, let's look at the unsigned case. The smallest number we can represent is obviously 0, because we can't represent any negative numbers. But the largest one we can get is if we pile in all the 1s we can into that number. So you already saw it with a 4-bit number is f, 1111, has value 15, which is 2 to the 4th minus 1, not 2 to the 4 minus 1, 2 to the 4th minus 1. And so, in general, a bunch of 1s will be something that's almost a power of 2, but not quite. Similarly, we can think about 2's complement numbers. We can have just that negative bit be our only value. That's the most negative value we can possibly have. And the most positive value is if we turn off that negative bit and pile in all the positive powers of 2 we can. And it will be, in this case, 2 to the w minus 1 minus 1. And we can also, if we turn on the negative bit and all the positive bits, we'll end up with minus 1. Those sort of almost cancel each other out, but not quite. And in general, if you're seeing a hex number, it's a number, and it goes FFFF, blah, 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 blah. Most likely what it is a negative number. You know, you're looking at that whole string of 1s that are sort of the very negative value, a bunch of ones to sort of bring it closer to 0, and then it's whatever's left over. So, for example, to be more concrete, if we have 16 bits, then its largest value as a decimal number is 2 to the 16th minus 1 as an unsigned number, or as a signed number, it's 2 to the 15th minus 1. And similarly, a negative number, and it's a 0 followed by a bunch of 1s. Minus 1 is always a bunch of 1s, and 0 is always a bunch of 0s. So one of the curious properties of this is you'll see that there's this asymmetry in the representation, that I can represent a bigger in absolute value number as a negative value than I can as a positive value. So anyway, one figure out why there's sort of a missing positive number in there? Yes? Yeah, we need space for 0. Good. So anything with a 1 in its first digit, first bit, is going to be a negative number. Anything with a 0 in its first bit will be either all zeros, value 0, or a positive number. So that's why there's this asymmetry. And it's one of those things that doesn't really matter most of the time, but when it does, it's really an annoying thing. And as I mentioned, on pretty much any computer you encounter nowadays, you can have sort of words, you can operate on values that are either 8 bits or a byte, 16 bits, 32 bits, or 64 bits. They're all supported as data types in the language. And you can see now that if it's 32, as I mentioned before, 2 to the 32 is around 4 billion. By the way, I have a standard rule I like to use, which is, can you see this? That 1024 is about the same as the 1,000. It sounds like a kind of stupid thing, but when I see a number like 2 to the 32nd, and I wonder how big that is. Well, I see that it's 2 to the 30th, which is the same as around 10 to the 9th, plus 2 more, that's a 4, and so it's around 4 billion. Of course, not exactly, as you can see, but if somebody sort of wants to throw around numbers and you want to get some order of magnitude sense of it, this is actually fairly useful. So some people say that Microsoft switched to 64-bit machines because they couldn't represent Bill Gates' net worth as a 32-bit number. And the good news is we got a long ways to go with 64-bit numbers before that will become a problem. So in general, as I mentioned, there's this sort of asymmetry in the range. And of course, you also notice that on the unsigned side, we can represent a number that's, because we can use all the bits in a positive sense, we can get roughly twice the value out of it. So if you're being careful in C, or any language for that matter, you should not be too casual about assuming this range of numbers, there's never a guarantee that all machines out there that you might ever want to program use this 2's complement representation. So there's built into C, there's a special include library file called limits.h that define the maximum and minimum values of sort of standard standard data types. And those should be correct for the particular machine or compiler that you're working with. That said, a lot of people cheat and assume that it has these certain particular values. Okay, so one of the more curious ideas that we'll look at and we'll explore in various ways is what's the relation then? How do we, if we look at a given bit pattern like what's shown on the left, and in some cases we might think of it as an unsigned number and others as a 2's complement number, how do those two numbers relate to each other? And one property we'll see is it shown in green here is if they're non-zero numbers, then they have the same bit pattern, whether it's an unsigned or a 2's complement representation. But you'll see there's a sort of curious mapping between the unsigned numbers as they get bigger, when they have a 1 in their left position, and the corresponding 2's complement number, that they're actually, there's a delta there of exactly 16. And so there's some kind of curious properties of that mapping that we'll talk about. But now, as part of our experiment in making progress in education, I'd like to try this. And we'll see. I know you're going to groan, and we might all groan. So, if you go to the course webpage, which I hope you know already, and this is, I'll be amazed if this works. But there's a link on the left to Canvas, which, as you know, is the new version of Blackboard. And you probably have used it more than I have, because I never used Blackboard. But if you go to that page for this course, which for example, is called 1221, and it's listed as 18213. But if you go to there and click quizzes, it should be live. Day 2 binary.
Wait, so what if someone just goes in and does it like it's not on the left? What happens if they don't do it in the left?
So, unfortunately, I have an instructor view of this, and I have no idea what you're seeing. Have people found it? Does it work?
It works.
Are you finding some little problems that involve little bit problems? Does anyone need a pencil and paper? I don't have one. There should be 3 problems, each involving some bit things. And there should be some way I can watch your program. If you can't do it, there we go.
I think Canvas is currently getting over.
We're doing well. Oops. All right. Oh, don't worry about it. This is more of an experiment. I don't think you'll be able. You have to be enrolled in the course. If you're not enrolled in the course, just sit and relax. Look over the shoulder of somebody. It's not cheating if you do. So the good news is, you guys are right and the quiz answer is wrong. So basically everyone's fine. And I can also see you guys all, you, for the most part, did really well here. So. So I'm pleased to see that this stuff is for the most part, you guys have seen it, and I assume that anyone who got a wrong answer is more just sort of missed bit somewhere. So we'll keep, this is an experiment. I know that people have used this technology successfully in classes, so I want to give it a chance to sort of let it shake out. So getting back to the matters at hand then, there's a sort of quirky question, like in C, if I have some number x,
I can't read that.
in C, it's possible, when you just say int, it's a signed number. It can be positive, potentially can be negative. On most machines, but not all, not guaranteed, it would be represented as a 2's complement number. But you can also declare a data type, an unsigned data type. Implicitly, it will be an int. It's redundant, but you can also say unsigned int. So I can use casting to convert from a 2's complement number to an unsigned number. And you can imagine various conventions, like one of the way you might imagine this would be implemented is say, well, -1 is a negative number, and I can't represent that as an unsigned number, but I could give you a 0, and it's only off by 1. Should be good enough for partial credit, right? So you might think that's what it would do, but it doesn't. Does anyone know offhand what on most machines this value will be, what u will end up being? Yes.
2 to the 31.
Almost. 2 to the 31, it's actually 2 to the 32nd minus 1, right? It's like, if you imagine an unsigned number of all 1s, which is what -1 looks like, that's the number that it will be. So that's the right idea. So yes, exactly. That's the main idea, and it's kind of a weird idea to think about. But in general, what happens when you cast in C between signed and unsigned is nothing. The bits just stay the same. It's just all of a sudden I think of that high order bit as either positive or negative weight, depending on whether I'm thinking about it as signed or unsigned. But nothing changes. And so that's like really a way different idea than if I say and we'll cover floating point a week from today. If I say something's a floating point number, and then I convert it to an int, then something really happens. The bits really change. And that's actually a fairly important concept. But for now, we'll just keep track of these, this special case of between unsigned and signed. And this is true in C and in most other languages that support an unsigned data type. So the idea is, logically what we can think of it is, we're going to take a number that's potentially negative and morph it into one that's definitely not negative. But the rule we're going to do is basically to keep the bits the same and really just change the numerical value associated with it. And the same is true in the reverse direction. So if we look at our little table, going left to right, or right to left, if they're both in the range where the high order bit is 0, then the numeric values are the same. But if we're going in the range where the high order bit is a 1, then we're either increasing or decreasing the number by 16, or 2 to the W in this case. And what that means from a sort of pictorial point of view is we're taking the green range of numbers, the smaller order of magnitude numbers, and we're keeping them the same. But the numbers that were very negative before become very positive now. And then the same is in the reverse direction in the other way. And then this actually can have some kind of strange behaviors as a result of it. And in fact, it can lead to some really unpleasant results if you're not aware of it or prepared for it. And in fact, you'll find in some languages like Java does not even have an unsigned data type because there's so many perils of that type. So as I've been showing with my notation, you can explicitly do casting to convert. But there's also what's called implicit casting. For example, if I have, you see on the bottom, if I just say ux, some unsigned value, and I assign it to a signed int, it will do this. It's implicit casting. And of course, in this case, nothing really happens because the bits stay the same. But logically, I'm converting in some way between an unsigned number and a signed number here without anything being obvious that that's going on. Similarly, you can have a function that takes an unsigned argument and pass it a signed value. It might return a signed value, and you could assign it to an unsigned value. And those are all casts that get applied automatically from one to the other. And so again, that can cause some confusion. And just to give you a sort of illustration of why this can matter, one of the quirks of the language that I don't know why they came up with this convention, but they did, is if you're doing any operation where one argument is assigned and the other is unsigned, then the rule is you automatically convert that signed number to an unsigned one and then continue the operation. And that applies to addition, multiplication, and things, but also to comparison operations like less than and greater than. So just to illustrate what I'm talking about, these examples show what might be surprising results. And I'll mention in C, again, that anything you write as a decimal number is by default signed, unless you put a u, that could be either upper or lowercase u, at the end of it. So for example, if I'm comparing 0, the signed number, to 0, the unsigned number, what would the relative values of those be? Well, they're equal, right? Because they're both, if you think of their bit patterns, they're all zeros. And anytime for all the numbers reasonably close to 0, there's no difference between the unsigned and 2's complement representation. And you'll see on the right-hand side, it's key to understand how is this expression evaluated. And so what's really happening is, since this right-hand argument is expressed explicitly as an unsigned number, I'm implicitly going to cast this to an unsigned number and do the comparison. So if I compare -1 to 0, will it be less, greater, or equal? Less, right? Obviously. But what if now I put a little u on that 0? What will happen? I didn't change the bits, remember? It's going to flip there. What's going on? It's flipping because, remember, if I turn a -1 into an unsigned number, which I will for this comparison, because there's an unsigned number as the other argument, all of a sudden that -1 becomes a really big number. And so it will become a very large number compared to 0 that will be greater. What if I compare this, you'll recognize as T min, and this you'll recognize is, I'm sorry, this is T max, the biggest 2's complement number, and this is T min, the most negative 2's complement number. What the relation will be between that? Greater, right? Because a positive number is greater than a negative. But what if I put a u on that number?
So greater less than.
Yes, it would be less. So in this case, let me try this. Oh, this technology, I think that's used not working. It's going to try it. Let's see if this works. I don't really have like a blank sheet of paper though. So anyways, let's see what we can do. Oh, come on. Huh. Got to get out of this. That's no fun. This technology doesn't really always do what you want it to do. Shut up. I'm giving away all the cool stuff. But this one's pretty important. I want to show it. Remember that it's what I wanted to do. Do you think something is wrong? Is this funny? I'm not as incompetent as you might think. I really wanted that to happen. You draw a line there to say that bit pattern is a 0 followed by a bunch of 1s. And this one, the bit pattern is a 1 followed by a bunch of 0s. And so if it's an unsigned comparison, then the left one is smaller than the right one. But if it's a signed comparison, then the left one is a positive number and the right one is a negative number. And so it's the positive is greater than the negative. Huh. I don't know if that's a good thing or not. And so it goes. You can see these other examples are all instances of that. So this all is sort of an abstract thing, like, so it's actually a really good source of exam questions, but I won't let you worry about that quite yet. But it actually is a risk that happens in real life programs, that when you start using unsigns, there are certain things that you might be accustomed to that you no longer can do. So for example, imagine I have an unsigned loop variable I, and I want to do a countdown. I want to keep basically what's called a sort of I guess I call it a postfix sum. I want to take the values of an array and keep adding backward back to a of 0. And keep accumulating the values backwards. So what's wrong with this program? It's like seriously wrong. It's an infinite loop, right? Logically, it's an infinite loop because I is always going to be greater or equal to 0. I is unsigned. So what happens is I will hit 0, and then you'll decrement it. And what number will you get when you go, what will decrementing 0 give you in an unsigned number? Yeah, UMax, exactly. It'll give you a bunch of 1s. So all of a sudden, A of I is going to be at an address that actually doesn't exist on any machine that's been built as of yet, because there are no true 64. Well, no, it would exist on some machines, but it's a really big number, and chances are it's an out of bounds of your valid memory region, and it will hit what's called a segmentation fault. But so it will probably just crash as opposed to running an infinite loop. But in any case, it won't do what was intended. So you look at that, you go, yaha, you're kind of, what do you expect? You should never say I greater or equal to 0, because anyone can tell it's never going to happen. It can be much more subtle than that, though. Like way more subtle. And here's an example. Suppose somewhere I have this, a number I've defined somewhere as, because I don't want to keep using size of all over the place. So I just call it delta. And I want to do the same general countdown trick, something in this same way. I want to keep working this down until I'm within some range close to 0, but delta is a positive number, so I'm not actually going to ever let I go below 0. And I was a signed number in the first place, so that should be fine. So, anyone want to guess what happens with this code? Yeah.
Just sign and unsigned, so it all caches to unsigned.
Right. Very good. So, there's a couple things going on here, if you think about it. In C, I hope I don't have this. Size of operator, which is a pretty important operator, returns a value of type size underscore t. And that's defined on all machines to be an unsigned number that's sort of big enough to hold an arbitrary range of values for a data type. So it would be either 2 to the 32 on it when you're running 32 bits, or 2 to the 64 range. But the point is, it's an unsigned number. It's always an unsigned number. And so delta is unsigned, and now as you just said, so when I subtract delta from I do this implicit casting trick, and so the result will be unsigned. Even though it started with a signed number and I subtracted a constant from it, all of a sudden it magically, in the eyes of the C language, becomes an unsigned number. And so it's the same problem as before. It's never less than 0. And so it gets into the same problem as before. So my point being that these kind of, and it's a kind of bug that you can stare at this for hours, because mentally it's hard to remember this particular quirk of the language. So these are especially difficult types of bugs to deal with. Okay, we'll keep on looking at these sort of different bit representations and what they mean. So as I've mentioned before, we see already cases where we have some things are 8 bits, some things are 16, some are 32, and some are 64. And so there's quite a few operations that, for one reason or another, have to go between those different sizes. And so the general rule for, at least for the sign numbers, from going from a smaller representation to a larger one, is to do what's called sign extension, which again, offhand might not seem like a very useful thing. But the idea of sign extension, when you're going from a smaller word size to a larger one, is that you keep replicating that leftmost or sign bit. And the reason for doing that is, with this 2's complement representation, what it will do is it will preserve numeric values. So just as an example, if I'm taking a 5-bit number and expanding it to a 6-bit number, if that number is positive, I just want to stick a 0 in because I'm just, and you can, obviously that would make a difference. But the point is that's actually a form of a sign extension. I'm taking the leftmost bit and I'm copying it, which makes no real obvious difference for the positive case. But you see, it's also the right thing to do on the negative case. That if I replicate that 1, this is wrong. Minus 16 is not 1110, right? That would be minus 16 should be 101010. Minus 10 should be. Let's fix this. What do people think?
The fourth.
Right?
Yeah.
I want minus 16 plus 4 plus 2 is minus 10. Better? Hope I got it. So, I didn't make up this slide. It's actually a kind of, this example is actually pretty interesting to think about the logic behind this. So I wanted to make sure that the details are right as well as the context. But look at this case here. You see what happened is, in this 5-bit number, the most significant bit had a weight of minus 16. And when it becomes a 6-bit number, that minus 16 flips to be positive 16. But I'm adding another bit here with weight minus 32. And so if both of those are 1s, you see it kind of cancels out that, it cancels out with a net result of minus 16. And you think about it, oh yeah, that's actually the general principle behind it. And this sign extension, you can work it out that you can sign extend as far left as you want, and you'll get the same result, that you're introducing a string of bits whose total weight summed together is equal to the weight that the single bit had in the earlier number. And so that's the logic between sign extension of how you go from a sign number to a larger sign number without changing the numeric values. And that's what happens when you cast, say, from a char to an int. It will do that sign extension in order to preserve the value. There's other times when we want to kind of squish things down. We want to take a bigger number and reduce the number of bits. One thing you'll think about is, first is, wait a minute, you can't do that. That's what Claude Shannon's information theory told me is, you know, there's a certain amount of information and you can't go any smaller. And that's right. So what happens is somehow we're going to potentially lose information here. It can be even worse than that. We can not only lose something, but we can come up with something that seems to have nothing to do with the earlier value. But that's what happens when we go from a larger number to a smaller one in general. So for example, if we're going from a 5-bit number down to 4, and it's a signed number, what we're doing is we're taking that sign bit that was before and we're basically tossing that away. And whatever happens to be in now the new most significant position, all of a sudden we'll go from having a positive weight to a negative weight. And if the numbers are close enough to 0, you'll see that that actually is just fine. Whether it's negative or positive, I can basically afford to lose that most significant bit and still maintain my numeric value. Just as it's sort of the inverse of the sign extension operation. On the other hand, if the number I'm dropping is not the same bit value as the new sign bit, then I'm actually going to sort of do strange changes. So for example, this is 10. That one's correct. But if I make this a 4-bit number, mysteriously it's going to become -6, right? It's going to decrease by 16. And similarly, if I take a negative number, which is -10, I got this one right, and I drop off that bit, it's going to become 6. And the reason, of course, is I can't represent -10 as a 4-bit 2's complement number. My range is between -8 and +7 in this representation. And so what I did was basically flip it. So the point being that when you lose information, you're just going to change how you think about these bits. And it may or may not be the right thing to do unless the number is already fairly close to 0. Okay, that'll do us for today.